Let's do some analysis of the calculations we did to see what actually makes a difference in the inputs here. So let's look at the calculations for the office side of specialty flooring. We're still in the same project. As we figured out 1.9 tons, that's essentially because I mentioned earlier they only come in half sizes, that we're going to have to buy a 2-ton unit. So other things that we got a note here, that's 100 outdoor ventilation air. There's two different types of CFMs here. The outside ventilation air, which is what we calculated on the spreadsheet earlier, and that's 150 CFM total. That's the total for Office 127 plus 15 for Office 2, etc., etc. It adds up to 150. Then there's another CFMs here. These CFMs here, this column, design airflow CFM. That's the air that actually comes out of the air conditioning unit. The 150, it's air we pull from the outside and mix it. So the total air that comes out of the air conditioning unit and is distributed through the spaces is 665 CFM. That's what that is. This is 150 that we pull from the outside, mix it inside the air conditioning unit, and we get 665 out. Cubic feet per minute. So 1 cube of air, and we get 665 of those per minute out of the air conditioning unit. Now, how the loads are distributed, what happens? We measure heat in BTUs, British thermal units per hour. The load from the window and skylight, 352 BTUs. The wall transmission, 808. And what I was saying earlier, that we have one type of wall that works just for about everything. Our total is 14,899 plus 7654. That's about 22,500, if I remember correctly, and if I'm doing my math right, yeah, 22.6 thousand BTUs. It's only 800. The total load for the walls, it's only 800 out of 22,000. We could fiddle with that wall all we want, and we're not going to make a big difference here. The roof makes a difference. If you notice, it's twice the size of what happens through the walls. The roof usually makes a bigger difference than the walls because it's obviously more exposed directly to the sun. Window transmission, not a lot. This is in the office space because there's only one little window, right? And it's facing northeast. So a lot isn't happening in that window. There's no skylights, obviously, so the number's 0. There's no, I ignore the doors. And so 0 there. Floor transmission, there really isn't because even though we have 784 square feet, we're not gaining any heat from the floor. Emails coming in. How about that? Partitions and ceilings. Remember, we didn't do partitions. Overhead lighting. We have 2,600 BTUs, 2,700 BTUs of overhead lighting. Load. Electric equipment. 800 watts. That's 4 computers. 2,700 BTUs. 15 people. This is where it gets big loads start making a difference. 3,600 BTUs of sensible, and then 3,000 latent. So the total load by people is 6,750 BTUs out of 22. So that's a third of the load. So if you see where the wall transmission is 1/20th of the load, the people is 1/3 of the load right here. And now there's two different types of heat gain: sensible gain and latent gain. Sensible is the heat you can feel. So when you touch a hot rock, you can feel that it's hot. That's sensible heat. And the same way with everything. The window's hot, or the walls get hot, or the roof gets hot, etc. Latent is the heat you can't feel, but it's the heat we generate due to moisture. So we start sweating, we start generating moisture, and that's latent heat. If you notice, there's latent heat in people load, and then we come down here to other loads. The ventilation air for the outside air, 150 CFM, it also has latent load. It has more latent load than sensible load. So that's the humidity load, and this is the actual heat load of that air. And of course, if you notice, that's 45 plus 27. That's something in the round of 7,200, something like that, 73 or 7,400. So that's a big part of this 22,000 load. And so we go here and take a look at this to see if we made any mistakes. If for some reason this number was big, crazy big, we would try to figure out what happened. And we see here that we have 15 people. So if we remember correctly, that makes sense. 8 people in the break room, 8 people in the conference room, 2 people in the office. In that office, another 2 people. So that adds up to 15, I think. Now, the ventilation load, there's our CFM right here, 160 CFM, 150 CFM. So that makes sense. So we come in here to check to make sure we didn't make any mistakes. Another place we need to look, because sometimes the geographical location changes, then we'll go back and make sure that we got the right place selected here. This is the input we did, and the first step we did in doing the HVAC calculations program. We have 784 feet. And here's what it tells us about this part of the building. The load occurs. That means, when is this building at the worst condition? Sometime in June at 4 p.m. Under the at 92.5 degrees, when the temperature outside is 92.5 degrees outside, wet dry bulb. Maybe we'll explain wet bulb and dry bulb at another time, but these are conditions that occur in Charleston, South Carolina at 4 o'clock in June, so 92.5 degrees. There are, of course, times that it gets even hotter than that, but the calculations are done for, I think, cases that only happen 97% of the time. So there's a number there that we're required to follow. Of course, sometimes it feels like 100 degrees, so we just can't go and punch in 100 degrees, because air conditioning isn't sized for the super worst day of the year. It's worse for 97% of the time, or whatever that number is. So that's where that comes from. What else? It also tells us that the heating load occurs. Let me just see here. Yeah. Think right here, when it's 59.9 degrees outside. Doesn't tell us when. And I'm not sure why it does that. This is the calculation method it uses. There's a couple of ways to calculate air conditioning, and you can do all this by hand. And there's one called a transfer function method, which is what this program uses. Anyways, of course, we can look at these tables. We make sure that we got the spaces right. The break room was 79 square feet. If we remember, there was 2 rooms that were 159 feet. That was the one office, and then the conference room. There was the bigger office was 283 square feet. The 2 bathrooms, 54 and 50. Now, what happens here? I just realized that we're exhausting 75 from each bathroom, if you remember. If the exhaust is larger than the air we're bringing in, then we got to bring at least in the amount of exhaust. So that's why it's 150. And if we didn't have bathrooms, we'll be exhausting 27 plus 15 plus 50 plus 36. That is certainly not 150. It's more like 86 plus 15, that's 101, plus 27, that's 128. So we only need 128 CFM of outside air brought in, but because we're exhausting 150, we got to bring at least 150 in. So that's what happens with analysis. Let's take a look at, the second system, which was the system for the showroom. So this will be a little different. 11.2 tons, we're at 5,108 square feet, Charleston, South Carolina. The load occurs at a different time because the orientation is different. This load occurs here at 1,400 hours in July, not June. That's 2 p.m. in June. And if you notice, the temperature is a little different, 93.5 degrees. And the reason that is because the orientation of the building, the angle of the sun, and all of that. That varies based on your window exposure. It varies based on the building orientation and things like that. And of course, the shading has a lot to do with it. So what's happening here? 1190, and let me find that number. Yeah, 1190 CFM is what the outside air we put in. And so 1190 CFM of outside air and a total of 3440 CFM of mixed air. That's outside air plus recirculated air. What the air conditioning unit does, it takes outside air and recirculated air and combines it and cools it down to the right temperature. It cools it down to 58 degrees. That's what it comes out of the air conditioning unit. It comes out at 58 degrees, and by the time it leaves the registers, it's at a similar temperature, maybe a little higher because heat loss in the duct, or you have ducts in the attic, or things like that. Let's see what's happening load-wise. Okay, so it's 87 plus 47. That's 134 plus. So let's see, 134.4. What are the loads? It's a bigger roof, obviously, so there's more roof load. There's much more walls, obviously. I'm sorry, this isn't roof. This was windows. There's many more windows, so there's more load. There's more walls, obviously. A total of 2,800 square feet of walls exposed to the outside. There's a 5,108 roof, right? And 10,000 BTUs. So basically almost a ton of air conditioning just because of the size of the roof. Window transmission, there's no skylights. We ignore the doors. There's no floor transmission because we're on above ground, and so we don't gain any heat from the ground. Overhead lighting, it's larger, of course, because we have 1 watt per square foot, so we have 5,108 watts, which converts to 17,000 BTUs of lighting. That's a ton and a half of air conditioning just for the lighting load. And so if we want to minimize that, for some reason we want to cut back a little bit, we can really take a look at how much lighting we're putting in there and reevaluate this number and make it smaller with better light fixtures, more efficient. They use less wattage per lumen. Then we could probably cut that number down. Electrical equipment, we have 3 computers in there. 2,000. People, of course, more people. Here we go. 17,710. So that's a ton and a half of air conditioning just for the people sensible load. That's the heat that they generate. And then 9,200, almost 1 ton of air conditioning just for the load the latent load they generate, the moisture load they generate. What else happens here? Our biggest load, obviously, 23 plus 38. So that's like 40 plus 20, 60 and some change, right? 60,000 BTUs of outside air. That's 5 tons. 5 tons of outside air conditioning. That's bigger than consider this. The size of the air conditioning unit just to control the ventilation load, the outside air load of 1190 CFM, is bigger than most air conditioners in people's houses for ventilation load. And so we got to pay attention here that we're not putting too much outside air. This is a number we calculated, so we make sure we review this and that we didn't punch in the wrong thing. Garbage in, garbage out. So we got to go make sure that we punch in the right stuff. It's 1190 CFM in Charleston, South Carolina, and then it's 77 people. So those numbers are right. The rest, obviously, in order of, in some sort of order of what's worse, windows and roofs are usually worse. Walls are almost negligible because when you think we have 5,500 BTUs of a total of 134,000. We can do a lot of things to this wall, and it's not going to make one bit of difference when it comes to this total load. The overhead lighting, what is that? 10%. It's 17,000 of 130,000, so a little over 10%. Electrical equipment is not making a big difference. Some computers and one refrigerator is not going to make that big a difference in a building this size. The people and the ventilation load is where we got to be careful. Those are dictated to us by code. That table tells us how many people we got to have, and also tells us how much outside air ventilation load CFMs we're allowed to have. But we got to be careful with those, though. We make sure we punch them in right here. Imagine if by accident we added an extra zero here, and it's 11,900 CFM. This thing will skyrocket. But we'll be able to see that because we're studying this, and we'll be able to see that something's not right here with the numbers. Sometimes the numbers will jump at you, and then you can go back here and see what happened. And if you figure it out, then you go back to the program, change the number, run the calculation again, and you'll have it figured out. This is part 5. I'm going to conclude here with HVAC design. I probably missed a lot of things. I think I got the gist of it. And if there's anything that I didn't cover, I'll probably cover it in person with you.